Welcome to this post-lunch session, and today's keynote. We are extremely happy, and it's my honor and privilege to invite Professor Srini Devadas, who is a professor at MIT USA, and he has been a professor at MIT from 1988. And Professor Srini Devadas needs no introduction to this group, but I'll just, for the sake of formality, do my bit. So essentially, he essentially has got phenomenal contributions in computer architecture, computer systems, computer security, and applied cryptography. Professor Srini Devadas essentially has got several inventions to his credit, and on personal note, I would like to mention about physically unclonable functions, which we all know is a promising candidate for several, like authentication and, like security applications, key generation, and so on. And at the same time, I would also like to highlight that Professor Srini Devadas has 8 Test of Time awards given to papers for more than 10 years of beyond their publications. Professor Srini Devadas has, like several accolades to his credit, including he's a fellow of the IEEE and fellow of ACM. And he has got tremendous contributions in the overall gamut of like circuits, microarchitectures, and security applications. So with this, I would like to kind of invite Professor Srini Devadas to the podium, and the stage is already yours.
Yeah. All right. Thanks so much for that kind introduction. It didn't have to be that long, but. A real pleasure to be here. I have to thank Debdeep and Michael for the kind invitation, Reza, Camila, and Amir and the organizers for this beautiful event. As with most professors, students do the work, and we try to take credit, and give these talks. So I really have to acknowledge Daniel Sanchez, who's also a professor at MIT, who's a computer architect who led a lot of the work that I'm going to describe today. And Nicholas Samardzic was a student who graduated with a PhD a year or so ago. And Simon Langowski is one of my students. As you might have noticed, the title here is a bit aspirational. So I don't know what a Universal Cryptographic Accelerator looks like, but I know more about it than I did a few months ago. And hopefully, this talk will be thought-provoking, and I would be happy to answer questions about it and also talk to people offline. But I want to tell you about my thoughts on how we should accelerate cryptography. Let me just give you a sense of what I want to talk about today. I want to briefly touch upon a hardware for crypto for hardware success story. Maybe it is a little bit difficult to parse, but what I mean by that is hardware that was built to speed up crypto, which ended up affecting cryptographic design. And this is co-design at some level, and I think this is something that we should all do as we move on to the post-quantum era and think about accelerating sophisticated cryptography. So I'm just going to mention that. Ingrid gave a beautiful talk yesterday, and part of it was accelerating FHE. And so I went back and removed some of my slides that are going to be redundant. But I will say a little bit about that. Daniel and I and our students have done some work on it. And then talk really about this co-design aspect that I just mentioned, which is some work on ZKPs that looked carefully at the gamut of different ZKP schemes and tried to, from first principles, think about what would be the best scheme for hardware acceleration. And then, everyone's gung-ho about post-quantum, but I'd have to say number theoretic cryptography is still the most widely deployed, whether it's ZKPs and Groth16 or elliptic curve cryptography. And my thoughts on acceleration of number theoretic crypto really changed over the summer. And so this part of the talk is fresh from the oven, so to speak. And then briefly talk about some closing thoughts and next steps. What is this success story? I think you all know about this, but I want to describe it in a slightly different way. So AES has been around for a while, and at some point Intel decided to create the AES-NI instruction set, which became standard on modern CPUs. AMD put it in, and obviously AES custom hardware has been in smart cards and what have you for a while. It was meant to accelerate TLS and web browsing. But then, as I was teaching a cryptography class with a theoretical cryptographer, a lady by the name of Yael Kalai, I noticed that she was saying things like, oh, it's a PRG. Think AES. It's a PRF, a pseudo-random function. Think AES in terms of the implementation to these undergraduates who were taking the class. So what really happened was that PRGs and PRFs in the software realm are much slower than AES in the software realm. But because there was a hardware implementation of AES available, suddenly you could do PRGs and PRFs faster just by invoking this AES-NI instruction set. And it affected these theoretical cryptographers in the sense of at least how they were teaching things or how they felt like these basic cryptographic primitives needed to be built. So that was nice. And then the question is this sort of hardware for crypto for hardware success story applicable in other realms as well for other cryptographic protocols? And really the last 10 years have been incredible, right? In terms of the interest in sophisticated cryptography. And here are a whole bunch of different cryptographic protocols that I'm sure you've heard of. And a whole bunch of them are now deployed. People use PIR in large companies, even for within organizations. There's different access control. Oblivious RAM, which is similar to PIR, which obfuscates memory address patterns, is used in Signal, the popular messaging app. We know about some FHE deployments in not necessarily in large scale inference or AI, but in more limited forums. And ZK snarks are all around us in the cryptocurrencies like Zcash. And as I mentioned, there's been wide deployment of Groth16 and number theoretic cryptography. And some of this is certainly due to economic forces, but a lot of it is because the technology has improved to the point where there have been algorithmic innovations and hardware acceleration or other kinds of different forms of ASICs or FPGAs. And the world is a very different place than it was 10 years ago with respect to these protocols, which are really considered arcane. So I want to tell you a little bit about some work that Daniel and I and our students did on accelerating FHE. And this was really looking at it from a standpoint of, is it possible to build an ASIC, is it possible to build a programmable ASIC that would make FHE practical, right? Because the overheads are just staggering. I mean, there's, depending on who you talk to, you hear 7 orders of magnitude or 4 orders of magnitude. I mean, the people who say 4 orders of magnitude, like FHE better, but that's it's a lot. I mean, you go to different organizations or different communities, and 10% is a big deal, right? And now you're talking about 5 orders of magnitude. So something has to give with respect to getting this stuff used. You do have to reduce the overheads very substantively. And so you can argue it's the holy grail of secure computing or the holy grail of private computing. Really, it's a family of protocols, and I think you all know this, so I'll be quick. You have a function f, and you get to run that function on an untrusted server. And that untrusted server, let's say, knows the function. You can also encrypt the function. But let's just say that f is public, but the input to the function is secret, and you can do your taxes, online by sending in an encrypted W-2 or encrypted tax form. I have to remember I'm in Malaysia, and people may not know what a W-2 is. But your secret information is sent over, and then you get a number back, which is indecipherable to the server. And if you decrypt it, you get to know whether you owe the tax service or the government money, or they owe you money. Right? And this is perfect privacy, since the server never decrypts data. But I do want to point out, since we'll talk about ZKPs, is that there's no integrity guarantee associated with FHE. So the server could be malicious in the sense of send you garbage back, right? And so if you look at FHE, it's easy to see why it's so slow, why it would be orders of magnitude slow. If we just look at the schemes that encrypt numbers, or in this case, most schemes encrypt vectors of numbers, and what you end up having to do is choose a whole bunch of plain text values, and so you think of the n here as being something like 16,000 or something, so that's a large number, and you have these 8-bit values, and then you add a little bit of random noise to them, and then you encrypt it using a secret key that's only known to you, and you get this pair of polynomials. And these polynomials are huge. I mean, they have 16,000 coefficients, and each of these coefficients have 1,000 bits, right? And you're doing this for a small amount of plain text. So right there, a couple of things that are important. One is just the scale, which I've mentioned, and the other is that as you're operating on these polynomials, the amount of data movement that you have is huge and very irregular. I mean, it's regular in the sense that it's algorithmic, but from a standpoint of a CPU or a standpoint of a GPU, it doesn't really match the data path of either of these things. You want to add, multiply, and rotate. You want to add and multiply because that's the only way you're going to get fully homomorphic encryption. If you can only do one of them, you have just partially homomorphic encryption. And the goal here is encrypted computation. And these operations are fairly complex. And so you end up having, obviously, a pair of ciphertexts because you want to do something with a pair of numbers. And you end up, let's say, if you want to add them together, then it's easy. But if you want to multiply them, it's much more complicated. And you have things like key switching algorithms and so on and so forth. And as you can see with this picture, I mean, it's not a simple vector operation. And the data movement associated with producing this XY ciphertext, like I said, is irregular, requires permutations and rotations, and this is why CPUs and GPUs are pretty slow running FHE on even simple F functions corresponding to the F function that we have. The multiplication is, would be naively an order n square algorithm, but there's a nice thing called the number theoretic transform that's similar to an FFT that is essentially a convolution that allows you to do things in n log n. That's one aspect of it. The other part of it is the fact that you have large coefficients, which are well over 1,000 bits, and you want to do things like multiply these coefficients. No one, and you can contradict me in the Q&A, has built a parallel 1,000-bit multiplier on silicon because it would be too large. And also, as it turns out, because of the FHE algorithm, the bit width of the coefficients changes as the algorithm operates. And I'll tell you why in just a second. Those of you who know FHE know what I'm talking about already. So the thing that saves us here is the residue number system, or the CRT, Chinese remainder theorem. But the RNS is essentially something that says you have a composite modulus corresponding to these 1,000 bits, and then you can break things up and represent these things as residue polynomials, and then now you're working with 32-bit numbers and multiplying 32-bit quantities or maybe 64-bit quantities. So that saves you. And so now you have a situation where you're working in parallel. That's also good. So you have multiple parallel multipliers that are all small that are building these ciphertext polynomials. And that's the big advantage. And so there are other things that help as well. And so when we were looking at this a few years ago, thinking about a programmable processor that would run FHE for an arbitrary function f, we said, what are the characteristics of FHE that we could exploit? What are the things that we have to worry about? And we want to do this. It's programmable in the sense that we don't want to fix f. So there's been a bunch of effort on particular f, like inference, for example, on a small neural network, etc. So homomorphic operations, as I described, all rely on large polynomial arithmetic. The ciphertexts are huge, so data movement is going to be important. So things like permutation networks and transpose networks are going to come up later in the talk. But the one thing that is interesting that helps you a lot is the fact that data flow is completely static, because the fact is that you don't know what you're operating on. The server doesn't know what it's operating on. So therefore, it takes both branches of the if, both the then and the else, and it's completely static. And this means that you can schedule things in advance, and you can orchestrate the data movements and the computation in advance, and you can basically pipeline the heck out of this in order to get the lowest, the best performance. One last thing about FHE is these, going back to the coefficients, you have noise, and the way this works is you have ciphertext with some initial noise and small amounts of noise that is injected and large coefficient width, and then you, as you compute, multiplies are the bad operation. They get more noisy, and essentially what happens is you shrink the coefficients and you chop off the least significant bits. So you go from 1,000 to 900 to 800, and at some point you're going to run out of room. And if you run out of room, then well, you're dead. I mean, you've lost correctness, which means that you can't go anymore, and so you have to throw up your hands. So you obviously can't have that. So what ends up happening is the original implementations of FHE and even algorithms, they were somewhat fully homomorphic, and the other term for it is leveled FHE. And leveled FHE essentially says, I'm going to do this encryption for a certain number of operations, and then at some point when the server realizes that the number of bits in the coefficients is too small for correctness, it's going to basically throw up its hands and send the ciphertext, intermediate ciphertext that's computed, back to the client and says, hey client, please refresh these values and essentially decrypt them and then send me back new fresh ciphertext that I can operate on, and this goes on, right? And so now you can do arbitrary depth computations, and the theoreticians call this, for some reason, leveled FHE, but I'd like to think about it as limited depth FHE or somewhat fully homomorphic encryption. Unfortunately, with this, there's a large communication cost, and so the original processor that Daniel and I and students designed was something that handled leveled FHE, and it didn't handle what's called bootstrapping, which is an expensive procedure to refresh ciphertext directly on the server. And here you kind of see this sawtooth, which essentially says when the coefficient bit width drops below a certain point, we're going to essentially run this decryption operation on the server and then re-encrypt and then jack it back up to 1,000 bits or whatever. And that's a very expensive operation. And if you're able to accelerate that on the server, then you win a lot because you've reduced communication dramatically, right? And this obviously implies that we have to perform computations at multiple bit widths, but that's okay because we have RNS. The observations here are you can speed things up by having parallelism and pipelining, but going from 4G to 5G and increasing the bandwidth of a network is much harder to do. It still takes hundreds of milliseconds to get across the internet from one side of the United States to another, or from the United States to Europe, right? And Amdahl said a long time ago that accelerating computation it requires that you have to speed up all the computation that corresponds to your bottleneck. And so these two observations essentially tell you that you need to build bootstrapped accelerators if you really truly want to have a programmable FHE accelerator that has a hope of being deployed. And so if you kind of look at leveled FHE on the right and bootstrapped FHE on the left, you're spending a lot of time in communication in leveled FHE, but less time in computation because you have no bootstrapping to worry about. But what you can accelerate is the bootstrapping using computation as well. The communication is harder to accelerate. So if you go off and you accelerate the the computation dramatically, and that requires looking at looking at everything, and I'll get to that in just a second, you win, right? So I'm not going to tell you about the design of our leveled FHE accelerator, but I want to briefly tell you about the design of an accelerator that accelerated bootstrapping as well, that was published a couple of years ago at ISCA, and Crater Lake is the deepest lake in the United States. And so that's, it can handle deep FHE computations, not my name, but I guess I'm stuck with it at this point. But it's basically a vector processor that has extremely wide vector units. And I'm not going to spend a lot of time on it, but you can see things like change RNS base, automorphisms that are essentially transposes of a different kind. And this is a giant chip, which is 256 megabytes of a single level register file. It hasn't been built, but there are startups that are building things that kind of look like this, trying to accelerate FHE, as I said. But this was an architecture paper that was published, and I just want to give you a sense of the scale of speed up and the scale of the chip and the kind of modules that are in there. But at the end of the day, using a fairly simple design of 2048 vector lanes and this transpose network that allowed the convolutions and the automorphisms to run quickly, dramatically faster than a CPU or a GPU, you could essentially pipeline FHE computations and really get to the point where even in comparison to a 32-core CPU that had 64 threads with hyperthreading, you could run things 5,000 times faster. And now if you go to any architecture conference, there's usually a session on programmable FHE accelerators, and some of these ideas have stayed, and a lot of them have been replaced. But there's probably another factor of 10 out there thanks to clever architectural design over and beyond what we had here in Crater Lake 2 or 3 years ago. So this area is very fast moving. But I do want to point out that it's not that it's just parallelism, because a 32-core processor is your baseline. It's the fact that you're doing data movement fast. It's the fact that you have functional units that are different. It's the fact that you're doing static scheduling, and so on and so forth. Right? So much for that. This really was about taking what's out there, BGV, BFV, CKKS, and just figuring out how to run it fast. It really was a very satisfying project, but at some level, given my interest in applied crypto, it wasn't, I'll just say it wasn't an A+ project from my standpoint, just because we weren't doing algorithmic innovation. So not surprisingly, we switched over to started to think about ZKP soon after we'd published Crater Lake, and we actually, came across some really interesting issues that I'll get to, but I want to tell you what ZKPs are really briefly and what verifiable computation is. And you can think of this as the sister algorithm to FHE in the sense that it handles the integrity aspect. Of course, there's also privacy associated with zero-knowledge proofs, which we'll get to in a second. But when you think about verifiable computation, it's basically integrity but no privacy, whereas FHE is exactly the reverse. So same thing. You want an untrusted computer to run a computation for you and get a proof that it was run correctly, that is, it ran every instruction correctly. And these are out there in the world of digital currency and databases and federated learning, and I won't say much more. The little picture that you see up there with the FXW is the zero-knowledge part of it, where there parts of the input can be kept secret from the so W can be kept secret, but that's not going to be important for this talk. And the same deal, it's orders of magnitude slower. So we'd like to speed things up with hardware acceleration. Now, where is this useful? Well, it's useful if in scenarios where verification is fast, but the evaluation of F would be slower than what you would need to verify. So that's when outsourcing is important. But the proving time is going to be way slower than the, we'll call it the native evaluation time because the cryptography is going to cost you a lot, right? And most of you know this. I mentioned the zero knowledge, and things like machine learning model weights could be kept secret from the user who's getting the inference result back, and so there's the privacy aspect of it as well, right? And so it's possible that the client does not have F and can't execute F, and therefore is relying on the untrusted server to produce the inference for their particular query. So if you looked at the most widely deployed scheme, it's Groth16, which is amazing in terms of its proof size. You know, it's 512 bits, 784 bits, what have you. It's a compute-bound algorithm, and that you've seen a lot of papers on it already. I mean, I listened to one just before lunch, and it's got multipliers. It's got 381-bit. I mean, well, if you wanted to build this, you would have to do lots of things in order to speed this up. But the naive way of trying to speed this up would involve large multipliers. And if you look at ASIC accelerators, I mean, they're not getting 5,000x speedups on Groth16. For the simple reason. I mean, there's many reasons, but the simplest reason why you only get perhaps an order of magnitude, even if you compared to let's say a parallel multi-core CPU, if you built an ASIC, was because of this multiplication. Because you don't have RNS here to help you build small multipliers that can give you the elliptic curve operations, right? And I'm going to revisit that towards the end of my talk. But that was my thought, and that was the reason why certainly PipeZK that was published in 2021 was only about a factor of 5 faster than a multi-core CPU. So who would build an ASIC if it's only a factor of 5 faster, right? And nobody did. So looking at ZKPs, the world of ZKPs is incredibly rich. You have the interactive oracle proofs. You have different IOPs that take the function and put it into a polynomial structure. And then you have polynomial commitment schemes. And together they make ZKPs. And if you look a little closer at the PCS universe, you have curve-based ZKPs that are the ones that are most widely used, like Groth16, and you have hash-based ones that came out a few years ago, like Orion and Ligero, and lattice-based schemes that are not at the same level of maturity, but they hopefully will get there. And the latter two are post-quantum secure, so that's nice. And if you look at the acceleration aspect of accelerating curve-based PCSs and hash-based PCSs, there's downsides associated with the Groth16 variety that I've mentioned. And you also have a little bit more of a difficult time with parallelization because of data-dependent control flow. So when we looked at hash-based PCSs, we liked them a lot better because not only are the hash functions designed to have hardware-friendly implementations, they have tree and matrix structures for when you're doing many hashes in parallel that are easily parallelizable. So the downside is that the proof sizes, especially in comparison to Groth16, are much bigger, right? Think orders of magnitude bigger. So anyway, we decided that that wasn't going to stop us. We looked at different modular ZKPs and looked at a whole bunch and ended up zooming in on Spartan and Orion, deciding that they map well to hardware. So the Spartan IOP along with the Orion PCS was work done previously, not our work, though we did do some minor optimizations on it. And if you kind of look at the Groth16 and Spartan and Orion side by side, I mean, this is not a pretty picture. You have more computation in Spartan and Orion, and because the proof sizes are larger, the amount of data that goes back to the verifier is significantly larger in Spartan and Orion versus Groth16. But interestingly, if you bring hardware acceleration to the mix, you get something like this, which is you can just get orders and orders of magnitude speed up, 3-4 orders of magnitude speed up in the computation associated with Spartan and Orion if you're able to build a chip. Whereas it's much harder to accelerate Groth16 by that same 3-4 orders of magnitude. And so this was our realization. What was it? A year, maybe 18 months ago. And so we said, we think we can do this. Let's go off and try to design an accelerator that accelerates Spartan and Orion. And they consist of many complex algorithms, as you can imagine. But all of these algorithms are built on 5 low-level tasks. And you do things like sparse matrix vector multiply, sum check, the sum check protocol, which is essentially something that can be built into hardware quite easily, polynomial arithmetic that I've talked about already, Merkle trees that I think most people are familiar with, but they're essentially hash trees, and some error correcting codes, including Reed-Solomon codes, but there are many, many variants. So these operations are common to virtually all hash-based ZKP schemes. And not only that, some of these are common to the FHE accelerator that people have designed, and including Crater Lake. So I want to keep that in mind because that's going to be important, going forward. And so just to give you a sense of what happens here, you map constraints to polynomials using this sparse matrix vector. You commit to these polynomials using the ECC, Merkle tree, polynomial arithmetic, and sum check, and then use the sum check and polynomial arithmetic to actually check the polynomials. And if you look at what units you need, it turns out you need 5 units, and these are very similar to the FHE units. So now you're starting to see why the title of my talk was the title of my talk, because we're trying to do a few things here. We're trying to grow the set of algorithms that we can actually accelerate using the same piece of hardware, because we think it's going to be incredibly important if someone's going to drop $50 million on building an ASIC, that ASIC is going to have a lot of uses. And it's got to be programmable, but also have uses across different application domains. And going back to Amdahl, Amdahl essentially said, well, if you want 50x speed up, then you better accelerate anything that's 1%, 2% of the computation, and we obviously wanted much more than that. So it meant that all of these operations that you see here, you see the percentages that correspond to, on a particular benchmark, the percentage time that they take, and so we have to attack each one of them. So it's really, when you do ASIC design in this realm, you can't leave anything untouched. You have to accelerate everything. And so this particular accelerator for ZKP is called NoCap, was published a few months ago. It's a vector processor, like Crater Lake was, but except it's heterogeneous as opposed to homogeneous 2048 vector lanes. Supports many of the same operations. There's 2 big things that are different between NoCap and Crater Lake. The heterogeneity is one of them. In order to do modular multiplication and addition, you want to do this in parallel across as many lanes as possible. But when you have hash functions that are multiple words, and when you're doing NTTs and so on, we needed a different configuration. And so there's two modes of operation. There's different matching. Throughput is incredibly important to match data movement, and that's exactly why you have 2 different modes in NoCap. The nice thing about ZKPs as well as NoCap, and NoCap exploits that, is static control allows you to do all of these things, orchestrate all of these things in advance. You don't know what the data is, but you don't really care. And I won't say much about the memory hierarchy, but here's some pictures. I mean, these are obviously not detailed designs, but I really want to give you a sense of what NoCap looks like. As I said, it's 2048 lanes. Each of these entries now is a lane, and you end up shifting it into something where you're piping things through these 16 lanes and pretending that you have 128 lanes when you're doing vector hashing, whereas when you're doing the full polynomial arithmetic like vector addition, you use the previous configuration, right? So what happens if you build this and you simulate it functionally cycle by cycle? The original Spartan and Orion paper had a software implementation that we optimized and sped up by about a factor of 5. So that's your baseline. And then you compare that baseline, the optimized baseline versus the no-cap implementation, and you can get substantial speed-ups through this careful design. So I'm not going to spend any time on it other than saying this is some motivation for building this chip, and you need this level of speed-up if you're going to go invest money in building a chip. I don't think a factor of 10 or even a factor of 100 is going to be enough. The interesting thing here, which I do want to spend a minute on, is going back to the co-design aspect, the choice of hash-based ZKPs versus Groth16. So there is a downside to the hash-based ZKPs, a significant downside, which is why they're not used in blockchain, is that the proof sizes are orders of magnitude larger than Groth16. So if you really want to do a fair comparison of end-to-end latency, it's not the 586x that was just the proof generation time, but the fact is that if you want to go say, how long did it take me to get the verification across the internet, the server sent me the proof, and now I've verified it, the actual computation is not as bad as sending it over the internet, then this latency should be included. And that's what I call end-to-end evaluation. And there, no-cap is not 500 times faster. It's 20 times faster than PipeZK, which is obviously faster than a CPU, but you lose something. So this end-to-end evaluation sort of gives you a sense of the algorithmic trade-offs across elliptic curve PCSs and hash-based PCSs. So I think this is a rich area, and as I said, at any architecture conference now, it seems to have papers that certainly the FHE papers are pervasive, but also ZKP acceleration papers, including, of course, here. But I was specifically referring to programmable ASICs, which are usually published in conferences like ISCA and Micro. So what I have left to do is to tell you a little bit about putting all of these things together and really, delivering on at least at some level on the title of my talk. And so if you kind of look at different cryptographic protocols like FHE, hash-based zero-knowledge proofs, private information retrieval, which is really a special case of FHE, and the curve-based zero-knowledge proofs, and you look at the modules or the functional units that you need, this was the picture that we had, and this was maybe a few months ago. And the problem here is really the fact that you need wide integer modular arithmetic corresponding to curve-based zero-knowledge proofs. And so we felt like, it was nice that we were in the post-quantum world, but we wanted to accelerate the most widely deployed protocols. So I want to say a little bit and spend a few minutes talking about some work that we've done on accelerating number theoretic cryptography. And our goal here is to speed up kind of the most basic number theoretic cryptographic operation around, which is modulo multiply. Except that you now have a prime P that is a large prime, which is maybe 4096 bits if this is RSA, right? And the problem here is we can't use, if you just look at it, P is atomic, and we can't directly use RNS. And I think people have heard about Montgomery multiplication. This audience knows about it, so I won't say much, but you can do things without having to do division by operating in a special domain. And the Montgomery product definition looks like this, and you end up getting a result back that's in Montgomery form, and you have to do some work. But if you can continue, especially if you're doing exponentiation in Montgomery form, then you don't have to do this conversion back and forth. Right? So that's kind of the way the world is, and people use Montgomery everywhere, including in multiscalar multiplications and so on. But the question is, is there a world where you can pretend that the prime P is composite and use RNS? And it turns out, this wasn't us, there's an algorithm that's 30 years old, and maybe there's been a couple of papers in CHES, but not more, written on hardware implementations of this Posh and Posh algorithm from 1995 that essentially says, you can choose two composite moduli, M and N, that are larger than P, and then rather than having a T word prime, rather than having a 4096-bit prime, you could have many 64-bit primes, and the multiplication of those primes has to be larger than the actual prime you want to compute the modulus for, right? And this Posh and Posh algorithm uses the Chinese remainder theorem and has this particular flow associated with it, where you have a particular modulus m that, as I said, is larger than p. It needs to be larger than 8 times p. And you go compute very easily a times b in RNS-M, because that's essentially linear if you think about 64-bit multiplies as being constant time. And then you convert this product into RNS-N, which, by the way, this conversion change RNS base shows up in FHE algorithms, and then use an approximation trick to approximate the quotient, then convert the quotient back into RNS-M, and possibly apply a correction. So there's a whole slew, there's a little cottage industry of algorithms and a relatively small number of papers written on speeding up RNS Montgomery. And Simon Langowski, one of my students, was able to optimize state of the art. And his algorithm essentially has a computational cost associated with these 5 steps, where if you have a T-word composite modulus, so your original prime would have been T words, you replace it with a T-word composite modulus, and you need 2t squared plus 16t modular multiplications, one-word multiplications, in order to run RNS Montgomery. And so you compare that with 2t squared plus 2t for standard Montgomery multiplication, and so that's obviously larger. But the game here has always been that you get to parallelize and you get to pipeline. In this case, you can vectorize, you can use SIMD operations, and virtually all of these 2t squared plus 16t operations are vectorizable. And so this is not hardware design work at this point. It's simply algorithmic work and running code on a GPU or an AVX machine. And so you have parallelism in a GPU. So consider a GPU with many vector cores, focus on a single vector core, and you have 128 physical threads, and you could also have a larger number of virtual threads, but that's not that important. And there's tremendous parallelism in this posh and posh algorithm, the variant that as Simon came up with. So if you had T plus 2 threads, then you could run this in a critical path of 2t plus 2, and you can read the rest. But the sad part is that when t is large on a GPU, because you only have 128 physical threads, you run out of threads, right? It's not all bad in the sense that you can compare this to standard Montgomery, and so this is a straight software comparison against the NVIDIA CGBN library, which is up there on green, and that's normalized, and you essentially get a factor of 3 to 4 running RNS Montgomery on the prime sizes that you see down at the bottom. So maybe over to the right, you're doing RSA decryption, and you could be doing elliptic curve operations, somewhere in the middle. And so what you see here with TPI is 32 and 64 is the number of threads that you can exploit. And there's some vagaries with respect to this that associated with the memory of a GPU that I'm happy to talk to people offline about, but you can roughly see the point here is RNS Montgomery is vectorizable and you can get speed ups, but you run out of threads, right? But that brings us back to hardware. And you can build parallel multipliers of certain sizes, and we actually have done that or people have done that, and they're certainly in there in the designs that I've described to you, corresponding to Crater Lake and NoCap. So if you look at what you would do if you had RNS Montgomery and custom hardware, you could actually imagine building something that kind of looks like a systolic array or a tensor core that's ubiquitous in GPUs, except the interconnections are a little different. And you can get an order log T critical path using this parallelism in the RNS Montgomery algorithm, and the log T comes from the addition tree of logarithmic depth. And this hardware is in the process of being built on an FPGA, but it essentially looks like a grid of T plus 2 by T grid of multiplier units. And again, think of T as each of these is a word, and maybe T is 12, maybe T is 16, and the word size would be 32 or 64 or what have you. And then you have your addition tree, and now suddenly you can speed up modular arithmetic with large primes, and you could speed up potentially elliptic curves. You could speed up RSA, etc. So in closing, I just want to leave you with the thought that it might be possible that you could put all of these different units together interconnected in a certain way, and in addition to this no-cap architecture that we have, which needs to be modified a little bit, in order to go do FHE, you put in this RNS Montgomery unit, which is essentially a two-dimensional array of multipliers. But hey, I mean, we have multipliers inside of these little modules corresponding to the ZKP accelerator. So perhaps you just go, change those multipliers to not just do your normal arithmetic or normal multiplication, but also modular multiplication. And this is my modest proposal for a Universal Cryptographic Accelerator, with the stress on modest. But if people have $50 million to burn, then well, I have a use for it, right? So thank you for my attention. That's all I had for you. Happy to take questions.
I think thanks, Srini, for the talk, and we have 15 minutes for some sessions on question answers. So please feel free to ask questions. So I think before someone asks a question, maybe I have a quick one. So I was wondering that you mentioned in your FHE, right, about additions and multiplications and also shifters, right? So I was wondering, like, why do you have a dedicated shifter? I mean, because is it like to?
So some of the slides I commented out would probably have answered that question. So one of the things that is why are ASICs so much faster than CPUs for FHE, multi-core CPUs? And I think your question, it's a good question. It points to the crux of the matter. So you have to do things like permutations, but you're doing things like something mod 3 or something mod a small prime, right? And you have to essentially rotate a vector of 16,000, mod 3 or mod what have you. And there's these things called automorphisms, and then you also are doing things in the NTT structure. And it turns out that there is a certain structure associated with these algorithms, CKKS and BGV, and you can build essentially a transpose network where to do these things, you take a constant number of operations. So if you wanted to take, on a CPU, it would be order n time in order to rotate a length n ciphertext to be mod 3, right? You just go one by one, and then you go through the registers and so on. But if you build a transpose network, and it doesn't matter whether it's mod 3 or in the possibilities that you have with respect to this modular rotation, if you will, are limited enough that you could build a transpose network that does these operations that are required in FHE in constant time. Okay, and so that's kind of the biggest bang for the buck with respect to the speed up that you get from either a GPU or a CPU. So I won't call it shifts, right? There's obviously shifting, but that's actually relatively easy, and you can do shifters on a CPU or a GPU, but it's actually the automorphisms and the transpositions that are required, and that's why I feel you absolutely have to put these things into hardware at a high clock speed if you want to run these algorithms fast, right? Yeah. Yeah.
So there's one question.
Thanks for the nice talk. I have a general question regarding the architecture for FHE acceleration. So you started with instruction set extension, and now we also see people using RISC-V as the base and adding special instructions to to speed up FHE and PQC. So that's one way to go, right? So you're starting as a CPU and then adding stuff to it. There's another line of work where you're really starting from the algorithm and you make dedicated building blocks. I mean, like the papers that you showed. So from your perspective, which way do you think will be winning in the future, considering that algorithm is changing and all these new technologies in semiconductor, including HBM and memory, in-memory computing.
It's a great question. I mean, there's no easy answer. I mean, there's so you obviously there's Ingrid talked a lot about FPGAs. There's the FPGA route as well, which has the advantage that you don't have to drop tens of millions of dollars in building a chip. But on the other hand, there's the clock speed issue, and there's also the cost of the FPGA in the sense that you need a big FPGA. But directly answering your question, what is that you need for FHE? The question is, I mean, people talk about AI inference or inference, and the scale of things that are run on these machines are resonant 20. It's not an LLM. It's not a medium scale language model or what have you, right? So I do think this. Honestly, there's a lot of hype in FHE that probably will never come to fruition, just because the overheads are multiple orders of magnitude. So my personal belief is that you have to find a reasonable application. One application would be that there's two aspects to it, which is you want your query, your inference query, to be secret from the server, and then the server has a proprietary information that they want to hide from you, for example, model weights. And then let's say you have that app, and then you want things to happen fairly quickly. Then how quick is that? If for certain latencies, you have to have an ASIC. That's running at a few gigahertz. I don't think this RISC-V extension is going to work for you. But maybe there'll be other scenarios where you're willing to wait a day to get your taxes back, or willing to wait minutes, and it'll work out. I think it's going to get driven by essentially the applications that require this level of privacy for deployment. Right? But the numbers are staggering. I mean, it's instead of taking a second, it takes a day. So you got to shrink that dramatically. And my personal feeling is that you got to have an ASIC running at a gigahertz, and then have a large ASIC with a lot of parallelism in order to meet that goal, wherever the person is. Yeah.
Thank you for the wonderful talk. I want to hear if you have any thoughts about the tension that might exist at the application level between all this technology, FHE, zero-knowledge proofs, and, for example, TEs, trusted execution environments?
Yeah. Well, FHE doesn't give you integrity. FHE doesn't give you attestation. ZKPs give you integrity, but they give you some level of privacy. But again, they don't. I mean, how do you know what machine you're running on? So I do think TEs have other problems. TEs, as we've heard, and we have lots of talks on it. There's side channel attacks and so on and so forth. I do think this is going to get driven by the application that you want to deploy. Perhaps you'll use a TEE to aggregate in federated learning. And it's just going to do a simple thing, and those things are exposed, and it may get encrypted data, and then add them up inside of the TEE, and then send the aggregates back, right? I mean, people have written papers on it. So I do think that each of these technologies is going to have a place. I think there's going to be a mix of them, and examples we have a paper that just came out a couple of months ago in this conference called PETS, which talks about taking a commodity piece of hardware, basically a 2017 machine, and it could be later, and running FHE inside of a trusted execution environment, except that it's commodity hardware, and it only provides integrity. It gives you attestation and integrity, and so if you want to raise FHE to be malicious security, then maybe you'd use that, right? I mean, it's just a paper at this point. But you could imagine doing something like that, which obviously is a synergistic combination. I mean, it doesn't have to be a competition. I guess maybe the message here is it doesn't have to be a competition, right?
Yes, thanks for the talk. It's CHES, so I have to ask, do you plan to equip your Universal Cryptographic Accelerator with countermeasures against side channel attacks and the likes?
Yeah, well, that's a great question. Countermeasures. I didn't even know where to start. You know, it's a good question, right? So when I gave this talk, I think I gave I gave a version of this talk at Illinois, and someone said side channels, and then I very blithely said, oh, I don't care about side channels because we are running FHE. And then the person came back and says, what about the zero knowledge part of it, right? So there you go. So the FHE accelerator, was easy. We didn't care about anything being exposed because everything is being run on ciphertext, right? And if you're only concerned with integrity, then you don't need countermeasures. Which again, is the question: is it a malicious attacker who's injecting things or a passive attacker? So there's obviously a question there. I don't think it's going to be super difficult, given the static control flow here in these things. Everything takes a fixed amount of time. Even the RNS Montgomery, everything is fixed, everything is orchestrated. I think it's a harder problem to take Intel XGX and or its successors and make that side channel resistant than making this fictitious hardware that only exists on PowerPoint side channel resistant. Okay.
So one related question that I had.
Yeah.
Maybe it is already hidden in the details. Like, do you also integrate the noise generators, because that's a crucial component, right? Like how you sample the noise and.
Oh yeah, I mean, well, the assumption is that there'd be some hardware random number generators on this thing, right? Definitely, right? Yeah. Well, hopefully I answered the question. And if you didn't get good answers to my question because I'm holding back here, come offline, right? Vincent.
If you look at plain text operations, signal processing, they have a lot more complicated arithmetic than add and multiply. And for example, a lot of effort's gone into the floating point unit, right? So for example, if you look at square root, it seems like you'd have to consider many more complicated mathematical operations.
Yes.
Has any chance of being anywhere near.
One thing that is hidden in all of this, which actually goes back to the applicability of FHE, is the circuit abstraction, right? I mean, cryptographers love circuits. I mean, well, you guys love circuits too, but we're talking about different kinds of circuits, right? You're talking about taking a program and converting it to a circuit, and that circuit, is something that can be statically scheduled and so on and so forth. People don't talk about the overheads associated with that conversion, and Vincent's question is partly related to that, or definitely related to that, in the sense that there are certain operations that can't get converted easily, right? The more complicated the operation, the worse it is for the circuit. Those overheads you never hear about when you hear about the 100,000 or whatever it is. The fact that you're doing worst case performance by following both the the then branch and the else branch isn't an overhead that's talked about, right? So there's a lot going on here that is hidden under the rug that makes perfect sense for in an academic environment. But I think when the rubber hits the road and you want to deploy these things, you end up having to sacrifice perhaps countermeasures and sacrifice utility because you don't have the ReLU operator, right? You got to approximate the ReLU operator in the circuit that is being run, right? So there's a lot here. I mean, I don't have the answers, right? Yeah.
Any more question? Okay, so if not, maybe let's thank Srini for this wonderful talk.
Well, thank you.